Well, thank you. It's nice to see so many friends and colleagues and new people here. In fact, the person who's responsible for bringing me to Scotland in the first place is also in the audience. That's Steve over there. So it's nice to see everybody here. So yes, Quantum Wonderland. Apologies to all the quantum physicists in the audience, because you'll have heard it all before. So this talk is for those of you who maybe, well, it's not your speciality. And I'm hoping to give you really an impression of what excited me into this field to start with. Quantum mechanics, Quantum Wonderland. You might think that, well, quantum mechanics, that's our theory of nature at the most microscopic level. So when you go down to the scale of single atoms and ions and photons and so on, and you might think it doesn't really matter for our daily lives. And many people get excited about, say, astronomy and these things. However, quantum mechanics can be just as exciting, if not more, in my opinion. And it really is something that fundamentally affects our daily lives all the time. So quantum mechanics is really everywhere. So as the introduction was saying, we wouldn't have computers, smartphones, any electronics without quantum mechanics. It's really because of our understanding of how matter works, and when you put atoms together, what kind of how does that behave? And that's what quantum mechanics tells us. And without that, we couldn't build all these things. So here you also see, here you see a laser. That's as well another example of quantum technology. Here's a really tiny laser. That's a semiconductor laser diode. I was raiding the internet for public domain pictures, and as you can see. So really, quantum mechanics is everywhere. We rely on it every day. Another example would be timekeeping clocks. So these two pictures show atomic clocks. This one, which is kind of table size, and then a tiny one. And these both work. In a clock, you have something that ticks. It could be a pendulum, for example, in a basic kind of clock. In atomic clocks, what ticks is the atoms themselves. So defined by the energy difference of atomic levels, you get an extremely precise pendulum. And that's how we do our timekeeping. And that's how GPS can work so well. That's why your smartphone can tell you where you are, because it relies on the timing signals that we get from atomic clocks. So you have the timing signals that come from satellites, and if you don't know exactly what time this signal arrives, then you won't be able to calculate how far away the satellite is, and you'll get your position wrong. So the accuracy of GPS rests on accurate timekeeping. And if you can make the clocks smaller and better, then your GPS, including lots of other things, will become better. So really, this kind of stuff is things that we use all the time. There's lots of medical applications. So MRI scanners, for example, magnetic resonance imaging, that relies on atoms interacting with electromagnetic fields. So atoms in your brain, and you can image then what goes on inside your head. Currently, these devices are kind of big, expensive, and bulky, and you'll find them in major hospitals. However, this is a soundbite from the report of the UK Quantum Hub on sensors on metrology, and that says that, well, an affordable quantum technology sensor for MRI scanning can become a reality within 5 years at approximately £30,000 for a GP version. So if you can make this technology smaller and better, as some people are now currently working on, then this machine could be something that's very small, cheaper and portable, and that could have huge benefits. So all these kind of things, this is something we have already. That's quantum technology that we have already, and now we have a kind of a second generation of quantum technology that we're working on. And in fact, the UK government, a couple of years ago, announced they're spending £270 million on developing the second generation of quantum technology. And this quantum hub on sensors and metrology is just one of 4 hubs that are operating in the UK. I'm part of a hub that works on quantum communication. I'll be mentioning that a little more. So this is really exciting current research, and we might see real technological benefits in the next few years. Okay, so quantum mechanics is really math. So the language of quantum mechanics is math. However, I won't be showing you any more equations than that. But you could argue that to really understand precisely what quantum mechanics is and what it tells you, you can't do that without also doing the maths. And you can only get so far if you use analogies which are everyday analogies. But you can get some sort of understanding of it still. So that's what we're going to do. So these equations for the physicists, that's the Schrödinger equation, which governs the time evolution of the wave function, for example. But I won't be showing you more equations. Okay, so quantum mechanics is about just over 100 years old. So in 1900, or maybe 1899 actually, Max Planck had this idea that if you assume that light comes in quanta, in packets, then you can explain certain features in spectra of hot. When you heat things up, they emit radiation, they start shining. And to explain that, it didn't quite work until he assumed that light comes in packets. And in 1927, various people contributed to this theory. In 1927, there was a conference, a 5th Solvay conference, where all the kind of important people, you see here Einstein, you see Paul Dirac, that's Niels Bohr, there's Schrödinger, there's Heisenberg, there's all the important, Marie Curie is there as well. She seems to be the only woman. On the other hand, she had 2 Nobel Prizes. I think there were 20-something participants, and something like 17 of them went on to win Nobel Prizes or had won Nobel Prizes. 17 of these lots. Quite amazing, yes. And at this conference, they sort of discussed and finally came up with what we call the Copenhagen interpretation of quantum mechanics, more or less. So quantum mechanics, basically everything seems to be fuzzy. That's what this quantum mechanics seems to tell us. You have uncertain relations. You can't determine precisely both position and speed at the same time. How many in the audience have not heard a version of the joke where Heisenberg gets stopped for speeding? Or has everybody heard this joke? No. So there's loads of versions out, but in one version of it, Heisenberg gets stopped for speeding, and the police officer asks him, so do you know how fast you were going? And Heisenberg answers, no, but I know where I am. Which is to say that, well, you cannot know your speed and your position precisely at the same time. And it's just not just because we can't measure precisely. It's really because they're not even precisely defined. And that's a little strange, maybe. And another thing which is to say that, well, for a long time there was a question, is light made up of waves or particles? And the same thing, well, matter, it seemed it's made up of particles. But then you can see strange things such as interference, also with matter. So interference is you have a wave, and if you take, well, you have 2 waves, and if you superpose them, you add them up, under certain circumstances, the values and the maxima and minima could add up, and you get like a stronger wave. Or if you shift the second wave, what happens is they can also cancel out. So you shift the second wave, you might also get nothing. So that's interference. And what happens is that you can see that certainly with light, if you shine light through a grating, or in the simplest case, just two slits. That's called the double slit experiment. But you can also see that with matter. So these pictures show interference of electrons, and it's a case where you are sending electrons to a grating, and you are sending electrons through a grating. It's not a very high intensity. So at any one time, there's just one electron going through the grating. But even so, and then the electrons start to arrive at the screen. So first you have just a few spots here on your screen, and then there's more and more spots. And when you wait, you have this interference pattern building up, which tells you those electrons have to behave like waves. So somehow each electron, although we tend to think of them as particles, they can also interfere, and they can seemingly interfere with themselves. So quantum mechanics seems to tell us that things can be both waves and particles, and it depends on your experiment which aspect you'll see. And you can also, if you start to try and measure where your electrons go through the grating, if you get sort of not quite complete information about that, what you will see is your interference pattern will degrade. It'll start going away. And when you determine precisely where your electron went through, then your interference pattern will go away. So it sort of depends on what you do in your experiment, what you see. As you get the answer, you get an answer corresponding to the question you're asking. And that seems a little strange. It's not just single electrons that you can interfere. So this is a series of experiments in Markus Arndt's group in Vienna, where they're taking larger and larger organic molecules. So this is tetraphenylporphyrin. I'm sure it's not the largest one they've done, but here is this big molecule can also be sent through diffraction gratings, and you can observe interference fringes on a screen. So the question then is, how large objects can show wave nature and can be in superposition states? We don't really know the answer. And people are discussing, maybe you need to modify quantum mechanics. Quantum mechanics tells you that, in principle, anything could show interference. But we don't really know if you get to very large objects. This is just a technical question. How many people have heard about Schrödinger's cat? Some people. So this is this thought experiment where you have a cat inside a box, and there's a devilish contraption with a radioactive atom that might decay, and if it decays, it releases a poisonous gas and kills the cat. And according to quantum mechanics, the atom can be in a kind of superpole state of not decayed and decayed. And it follows then that the cat is in some sort of in-between superposition state of both dead and alive at the same time. And we don't know whether that's just, so we don't know if that really is just a technical question, that is just very difficult to build a box, but in principle you could, and you could have a cat that's both dead and alive, or whether there's something else that kicks in when things become as large as cats. But experiments like this are trying to get at that question. So these guys are taking larger and larger molecules, so trying to show that you can show that these things show interference patterns. And that's very fascinating, I think. Another thing that quantum mechanics tells you, or doesn't tell you, it doesn't tell you exactly what will happen. It just tells you probabilities. And that's can feel quite unsatisfying, but at the time of this 1927 Solvay conference, maybe, some people were saying at least that, that's not such a problem because, we might only get these probabilities, but we can only ever perform experiments with a large number of atoms and large numbers of light anyway, so it doesn't really matter. Quantum mechanics tells us the probabilities. Who cares about single quantum systems? The only problem now being then that now we can actually do experiments with single quantum systems. So this is a picture from Rainer Blatt's lab in Innsbruck, where they are building ion traps, where they can trap individual ions with electric and magnetic fields and keep them there and shine lasers on them and do things to them. And that's single atoms, single ions. Continuing the line of bad science jokes. You heard the one about the two atoms that crossed the road, and one of them lost an electron. And the other one says, "How do you know?" And the first one says, "I'm positive." Okay. Yes, so that's ions. They are charged, which means you can easily hold them in place with electric and magnetic fields. Here are some pictures that Stefan Kuhr, my friend and colleague at Strathclyde University, sent me. So this is what he's doing, is he's trapping individual atoms in a so-called optical lattice. An optical lattice is interfered light fields. So he crosses laser beams and gets essentially an egg box potential where he can put atoms. And these spots here you see are imaged atoms sitting in this lattice. So it's a single atom there sitting there and shining. So these are the crossed laser beams here. And you get your optical lattice inside there where your single atoms, you can fill it with single atoms. And you can do amazing things. This is some earlier work that he did where he's sort of writing patterns. He's placing single atoms in any kind of pattern he desires, even something rather quantum mechanical. So there's a psi here, like a psi wave function. So nowadays we can do experiments with single atoms and single ions and single photons. And this has led to a surge in people thinking about what you can do with single atoms and single photons and single ions. And it's led to the research field that became what I started working on, which is quantum information science. And it turns out that so all these nice thought experiments that people thought about in the 20s and 30s, I mean, they're nice. But now when you have the experimental ability to actually do these things, you can start thinking about loads of other things that you can do. And I'm hoping to tell you about some of them. But I want to make it a little more concrete with exactly what one is working with. So very often one works with light. So light is an electromagnetic wave. Maxwell realized, he wrote down, this was I think in 1865, Steve would correct me, where he wrote down all the equations, everything that was known about the electric and magnetic fields at the time, and put them together. So nowadays we talk about Maxwell's equations, we mean 4 equations. And then he realized that those equations had a solution, which was a wave, and the speed of the wave that popped out of the equations was the speed of light. And then he realized, maybe light is an electromagnetic wave. That's not at all obvious. And indeed, I mean, light is an electromagnetic wave, and you have oscillating electric and magnetic fields. They're 90 degrees to each other, usually. And there's something called polarisation, which is what we do a lot of the experiments in quantum information science with, is using polarisation. Polarisation is essentially this direction of this electric field. The direction is it's oscillating. So it could be, if you're looking, imagine you're looking on a light beam head on, so your polarisation could be horizontal or vertical, for example, or 45 degrees either direction, or any direction, actually. These are just 4 examples. So you could represent polarization with a vector because it's a direction. Now what happens if you measure polarization? That you can do using a polarizing filter. So a polarizing filter would be something you have in good sunglasses as well. It's essentially, I've drawn this with sort of stripes on. It is essentially, a polarizing filter is essentially like a grill, if you wish, but on a scale that suits the wavelength of light, which is small. But it's essentially very tall molecules. And what you will find if you try and pass a light beam through such a material is that depending on the polarization, it might pass, well, it will pass or not pass. So if you have light that's polarized along this direction here, then you can orient your polarizing filter so that the vertical component passes and the horizontal doesn't. So it gets extinguished. And if you repeat the thing, and these projections, I mean, how much light you have on the vertical and horizontal direction is going to determine, I mean, the vertical bit gets through and the horizontal one doesn't, right? And if you do that with a single quantum of light, so these are a single photon, so these packets of light that Planck thought, oh, they must exist. And indeed, we know light does come in quanta. If you do this with a single photon, then you can't split a single photon. So a single photon will either pass or not pass. And quantum mechanics doesn't tell us whether it's going to pass or not for an individual photon. It just gives us probabilities. So here we're back at these probabilities. So we can't know, it seems. At least quantum mechanics doesn't tell us whether it's going to pass or not. Moreover, afterwards, you see here that if it passes, it's going to come out vertically polarized. Well, how the direction is depends on, you can turn your filter around and you could sort of, you could arrange it so that, well, it's the horizontal one or the 45 degree or any direction you like is the one that would pass. But here it's the vertical one. So if it passes, the photon's going to come out vertical. And you don't know anymore what direction it was originally polarized on. And you can, in fact, show that, well, there's no way of getting to know exactly what the polarization was. You can just do this kind of yes-no experiment. And you can't get perfect information if you don't know what this polarization direction is. And you just have a single photon. You can't even, in principle, learn exactly what it was. And moreover, it came out vertical. So the measurement changed what it was. So it's a little like if you have a glass of wine, as I hope you will have later on, and you're trying to see where it is by throwing golf balls at it. And you see, by how the golf balls are deflected, you can say where the glass was. Because it really was, it will be knocked over and you'll spill the wine and so on, and that's no good. So the measurement will affect what you're measuring. And if you're measuring something very small, that effect is going to be noticeable. So that's what happens for our single photon. We can't measure it. We can't learn anything about it without affecting it. And that's essentially what gives you quantum cryptography. So if you have two people here, Alice, since this is Wonderland, and Bob, if they send single photons to each other and try to communicate that way, and you have somebody in the middle that tries to measure, they will mess up the polarization of the photons that Alice is sending to Bob, and they can tell if somebody was listening. So, because it's not possible for anybody to learn anything about the polarization of the photons without messing them up. So that's essentially, in a nutshell, why quantum cryptography works. And you can actually build systems that do this for you. This is an example of equipment built by Toshiba, who have a research lab down in Cambridge, and we're collaborating with them in the UK Quantum Communication Hub for quantum technology. So what would you do then? Alice and Bob would use these boxes to not send their message. If they have a secret message they want to send, it's no good if somebody might be listening, and they will notice if somebody was listening, but then, okay, their message is out. That's no good. So what they do instead is they use this quantum crypto system to transmit random gobbledygook, i.e. a secret key. But it should be random. But they then afterwards, if nobody was listening, they both know that they have the same bit string, and nobody else can have any information about it. And then they can use that to decrypt and encrypt messages. And this is currently the only known way, using a secret key to decrypt and encrypt in this way is the only way you can get perfectly secure encryption, meaning that if somebody intercepts the encrypted message, they can do no better than guessing if they want to learn what the real message was, the plain text. And current ways that we're using for encrypting messages, they don't work like that. They rely on things being hard to compute instead. So decrypting the message is in principle possible without knowing anything, any kind of secret keys or anything, but it just requires, we think, too much computing power to do so. That's how our crypto systems, the ones that we are using, that's how they work. But if you use quantum crypto to share a key like this, you could do something which is kind of perfectly secure, if you wish. So there's also other things you can do, which is something that I've been working on quite a lot, or me and my group members, in these last few years. So not aiming at encrypting a secret message, but instead it's something that we use a lot, which is called signatures. So you have a message, you want to send it to somebody, and the signature can ensure that it's not tampered with or changed. You can encrypt it as well. Encryption alone also doesn't ensure that nobody's changed your message. Maybe they just change it and you don't know. They don't learn what it is, but they can change it. So a signature will guarantee that nobody's changing your message. So Alice can send a message to Bob, who can check that, yeah, it really came from Alice and nobody seems to have interfered with it. So Alice could say, Bob has the bank, say. Alice says to Bob, please pay Charlie $100 million from my account, well, or whatever. Or no, yeah, it should be the other way. Charlie has the bank, and Bob gets essentially a signed check by Alice saying, oh, Alice says that Charlie, the bank, should pay Bob $100 million. I said dollars because the pound is just going down these days, so it's not worth much. Anyway. Yes, so Bob can check that this message is really coming from Alice and nobody's changed it. And he can also, he can take the message to Charlie, and he can know that Charlie will also agree and actually give him the money. That's what a signature does for you. We use it all the time in email, online banking. Anytime you buy something over the internet, you will use this type of thing. So this is work that we've been doing. There's quite a few people involved here. We have both theory and experimental work on this. And we have collaborations with Toshiba in Tokyo and Germany. So here is, don't worry, this is just to show you what a recent experimental setup for an experiment doing quantum signatures looks like. So this was done in Tokyo in real installed optical fiber. So this is Alice. So what this piece of kit does is she's just essentially preparing different quantum states of light, and they get sent to Bob and Charlie, who measure. And they can be sure that nobody is listening, because if somebody would be listening, they would disturb the state of the light that's being sent. So that's essentially how it works. And then, of course, to make it really work in practice, you need all these sophisticated machines, because if you are going to send very weak pulses of light, they are very fragile, and you have to have very good detectors to detect them. So in practice, this is quite difficult to do, actually, and you will have limits on your data rate and limits on how far you can go. So that's what all the experiments in quantum cryptography worldwide is trying to do. They're trying to push this, higher data rates, longer distances. So that's where there's a lot of work to be done to get it up to sort of usable speeds and distances. Here is another example. This is our collaboration with Max Planck Institute of Light in Erlangen. So there they did a similar thing. So Alice is preparing some quantum states. And in this case, it's not an optical fiber, it's a free space, 1.6 kilometers between two buildings. So they're sending really faint light pulses through air with all the smoke and what have you and clouds and so on. Well, maybe not so many clouds at that level, but there's just stuff in between, and they can still manage. Bob and Charlie then measure at the other end, and they can still establish some sort of secret key for use for encryption of messages or signatures or something. So this stuff really works in practice as well. Right. I should move on. I have to talk about quantum entanglement as well. So quantum mechanics tells you only probabilities. And you can make quantum states that are like, if you imagine you throw two dice, and if you'd have a pair of dice, and every time you throw them, they come up with the same number. So an entangled state is a little like that. So you could imagine now, it's possible to prepare two photons in a state so that if you measure their polarization, the results always come up opposite. So one could be horizontal and one could be vertical, or the first one might be vertical and the second one horizontal, or these two directions. But every single time you measure, you need to prepare a new state, of course, every time you measure, because you destroy it when you measure. But never mind, every single time you prepare a state and you measure, the directions come up opposite. But, so I should say, that seems, maybe at first thought, it seems that you could maybe transmit a message. These two photons, they could be very far apart. And it seems that maybe I can transmit a message instantaneously. Yes, well, if I measure one photon, I'll know immediately what the other one would be. But my result is random. So I can only transmit a random message, if you wish. So you can't, in fact, you can't transmit any information like this. You can still use it for interesting things. But to illustrate, you have to have some audience participation in this type of talk, usually. So I need 2 volunteers. You can be one. Or any volunteers, I don't know. So I've got these 2 envelopes. This is just to illustrate. It's going to lead up to quantum teleportation, but I promise you'll be home for tea. Yeah, I promise you'll be home for tea. I've got two envelopes and 2 pieces of paper. And there's a purple piece of paper, and there's a yellow piece of paper. And I'm going to put each piece of paper in an envelope, and I'm going to mix them up, so you don't know which is which. And I don't know which is which. And I'm giving one to you, and then another one to, who wants an envelope? Derek, you can have an envelope. Please. Right. So this is to illustrate a correlation at a distance. So if you now open your envelope, do you have it still?
Sorry?
Do you have your envelope? If you open it, yeah?
I did keep it, yeah.
Yeah, you can keep it, actually, yes.
So do you want me to show something?
Yeah, just check your color of your paper.
Secretly? So I know the color, yeah.
Yeah, you know the, well, yeah, you can show people, well.
Okay.
And now, do you know what Derek's color is?
Yeah.
Yes, instantaneously, of course. So there's nothing.
Unless you're a magician.
No, this is no trick. So this is just to show that this kind of correlation at a distance is nothing strange. So this fact that your polarizations are always opposite, correlated, that's nothing strange per se, as your envelopes show. But with your envelopes, those pieces of paper were yellow and purple all along. And quantum entanglement is a little stranger than that. So the individual polarizations, I think you can safely say, well, quantum mechanics doesn't tell you what they are until you measure. And now the question is, yeah, you can sit down if you want. You can keep the paper. So this thing that quantum mechanics doesn't tell you what those individual polarizations are before you measure. That's bothered many people, famously Einstein, who says, well, quantum mechanics is not complete because of that. It doesn't tell you exactly what those polarizations are until you measure. And maybe you can completed. So Einstein believes the whole description of the physical reality can be provided eventually. So the question is, do the photons carry with them the results for all possible measurements that you might perform on them or not? And incidentally, Einstein wasn't at all happy that the New York Times wrote about this. So the story was leaked by Podolsky, who was his colleague, and Einstein wrote a very angry letter to the New York Times afterwards, and he was saying that he doesn't like his research to be sort of written about in the secular press in this particular way. And if New York Times is the secular press, I think it follows that the sacred text is the Physical Review. Maybe. Anyway, so the question is, do the photons carry with them these results for measurements you haven't made? And it seems so, because just like the envelope, that you open one of them, it's yellow. You don't even need to look at the other one to know it's purple. So with a photon as well, I measure one of them, it's horizontal. I don't even need to make the measurement to know that the other one would be vertical if I would measure it. So surely that verticalness, if measured in that particular way, that verticalness is something the photon must carry with it. Because those two photons could be far apart, and surely me measuring this one on this side can't sort of affect the other one in any way. So surely it must be carrying with it what result you would get if you would measure. So that's a perfectly reasonable and rational assumption. However, along came John Bell, who took those two assumptions, and instead of a more kind of vague argument of surely this must be the case, he took those two assumptions that things are real even if you don't measure them, and also that you don't have, things are local. So if I do something to something that, so one of the photons, that doesn't affect the other one. So reality and locality, he took those two assumptions and he managed to write down a precise mathematical statement, the so-called Bell inequality, that you could test in experiments for how correlated things can be with each other. And those are called Bell inequalities. And now you can make experiments to test them. So that's what we did. Actually, Tourmichet is in the audience. I see. Yeah, I got a smile there. So this is an experimental setup to test the so-called Bell inequality for whether, so there's some photons generated by this laser here. It goes through a nonlinear material, which has the property that sometimes a photon will get converted into two photons, and they are entangled. So this is a way of making entangled pairs of photons that go along here, and there's a beam splitter here that directs one photon one way and the other one the other way. And then you have these things called SLMs, spatial light modulators, which essentially they kind of imprint a face on your light field, and you can decide how to measure your photons. And then you have detectors, and in the end you are just writing, you're sort of detecting when you get counts, when you get a click here and when you get a click here, and you're building up this. It's called correlation functions, and you're checking how correlated can these photons be, how correlated are they, and you're checking this particular Bell inequality, and so you're essentially asking, is it consistent if I assume that these photons, they carry with them the results they would get if you measure them in a particular way. And you will find that, well, okay, by the way, so this experiment uses orbital angular momentum of light. Steve in the audience is kind of a, well, it was realized quite late that light can have orbital angular momentum. And this nice animation, which is, I think, from University of Glasgow, Miles Padgett's group. So this shows you phase fronts of light. So the one here with L equals 0 is just ordinary normal plane waves. And for other, so L, the orbital angular momentum, quantum of orbital angular momentum, L can be any integer value. And if you look at how the sort of light looks, it looks like pasta spirals, more or less. So you could say it's light with a twist in its tail. Possibly that was coined by Miles Paget? Yes. Yes, I wasn't quite sure, but Steve will know. So Miles, Steve, and Les Allen was kind of pioneers of working out the details of orbital angular momentum of light. So that's what we're using in this experiment. And you will indeed see that when you write down, when you calculate what you get for this quantity in the Bell inequality, so if things are local and real, this thing can't be more than 2. And you will find that when you do your experiment and you measure, it goes above. And it's more consistent with quantum mechanics. It's not consistent with things being local and real. And this persists until, in this case, 11 dimensions. So that means that we have 11 different values of orbital angular momentum involved. So this is a high-dimensional entangled state. And the kind of amplitude, the intensity distribution of these beams made a really nice cover for Nature Physics in September 2011. So this tells you, and many, many other experiments, this was by far not the first experiment and not the last and not the best, that shows you that nature is not consistent with things being both real and local. And we don't really know which assumption it is we have to give up, or maybe both. So that's work in progress for people doing experiments in kind of fundamental quantum science. And it's really kind of mind-boggling to think that it might be that before you make a measurement, even though you're 100% sure what outcome you would get in the measurement, maybe that property is not real, it's not there until you measure. So is the moon there unless you look? I think that was said by Einstein. So there was this dialogue between Einstein and Bohr. So Einstein asked Bohr, is the moon there unless you look? And Bohr was of the opinion that, well, it doesn't make any sense to ask a question. If you don't look, you don't look. So that's the kind of, yes, it's quite fascinating, I think. Okay, so what fun things can you do with entanglement? You can do something called quantum teleportation. So this will be like, really in a nutshell, a little simplified, but I think the essence of how it works is there. So you could set up this entangled state then of 2 photons, which you know they will have opposite polarization. So no matter what they end up being, they will always be opposite. And then you have this number 1 photon here, which has some polarization. You might not even know what it is. And as we were just saying, if you don't know what it is, you can't even in principle measure and get to know exactly what it is. So it just has some polarization, but you don't even need to know what it is. Now you can make a measurement on these 2 photons here, and you can ask, is their polarization opposite or same? And 1 and 2 are in the same lab, and 3 might be far away. And then if you get result opposite, then, so these 2 are opposite, and 2 and 3 were opposite to start with, then it turns out that 3 ends up being the same as 1 originally was. So now you're done. You've transferred the state of your photon number 1 over to the state of photon number 3, just like that, without actually sending it over. However, you could get the other result. If these 2 are the same, then this 3 ends up being opposite to what number 1 was to start with. So what you need to do is you need to flip it, and then you're done. So that's essentially how teleportation works, quantum teleportation. So you can transfer the state of photon number 1 over to the lab where photon number 3 sits without actually physically sending it over. That's teleportation, isn't it? There is one thing to note, though. You need to know whether or not to flip this one. If you don't get that phone call saying, oh, you need to flip your photon, or oh, you don't need to flip your photon, you just have a completely messed up state. So you need to get that phone call, but it's only a yes, no, flip or not flip outcome. And that's not enough to tell you exactly what that polarization was. Yes. So you don't, again, you don't transmit any information unless you have that phone call coming over. So again, you can't transmit any information faster than the speed of light. That's fine. Quantum mechanics will always obey that, in fact. You have all these paradoxes, but you can never use them to transmit information faster than the speed of light or something like that. So it kind of narrowly avoids the things that's supposed to be completely impossible, but still manages to be very interesting. Okay, so how about teleporting humans? In principle, you could do that with humans. It would be very difficult, though. You need to set up an entangled state of where every single atom in the body of somebody is entangled with an atom in some distant location, right? And then you need to do this opposite or same measurement. And then you need to transmit the data over. And to tell you whether or not to flip the states of those atoms. And if you think about just the data transmission part, I mean, never mind preparing this big entangled state or these many entangled states, that would be really, really difficult. But just transmitting this data, okay, so how many atoms do we have? Well, Avogadro's number is 10 to the 24. A terabit is 10 to the 12. If you calculate things, a year is about 10 to the 6 seconds. So if you transmit this data over, sort of a very conservative estimate, just transmitting 1 bit per atom, which isn't nearly enough in this case, that would take, if you transmit 1 terabit per second, I think I calculated 30,000 years. I made another calculation. I gave a public outreach talk 10 years ago, and then I calculated, okay, if you'd write that data onto DVDs, the stack of DVDs would reach from the Earth to the Sun. But this 30,000 years is bad enough. I would not wait that long. I would prefer to take the plane, I think. So yes, but teleporting humans would be very interesting because you could start saying something about, well, would the consciousness follow or not? So is consciousness just a consequence of exactly how the atoms in your body is arranged, or is there something more? So if you teleport somebody and then ask them how they feel, and if they still are the same person and so on, you could maybe learn something about that, but it would be a very difficult experiment. So I don't have really a lot more. I wonder, should I keep the 45 minutes or should I skip some things? No. So let's talk about interference again. So I mentioned this interference already. So this is to tell you about quantum metrology. Now, so an interferometer is something you can use to measure, say, small phase shifts or distances. If I move this mirror here, then I can make this. So here, if it's set up with these paths exactly the same length, then all the light you had positive, constructive interference here and destructive interference here. But if I change it a little, this will change, and you will have the probability or the intensity here will be proportional to sine square of half this angle and cos square of half this angle. So this is a setup by which you can measure. If you don't know what this phase shift is, you get a similar effect if you move this mirror a little bit. So you could imagine this mirror is the surface of some material, and you're trying to map out what it is like. And so you can do that with this type of setup. Or you could have a gravitational wave detector that works essentially in this way. And by sending light through and measuring how often or how much of it exits in each port, you can infer something about this phase shift or where this mirror was. And if you repeat this with n photons, the error in your estimate will end up being proportional to 1/√n. However, if you use entangled states, you can do better. So I could have, if I would have a very special beam splitter that in comes n quanta of light, and it sends them all this way or all that way, then you end up with having the error proportional to 1 over n instead. So you're getting a more precise estimate due to entanglement. And this, we can't make those beam splitters for optical signals, but here is an experiment where you had a molecule like this with 9 hydrogen atoms and a phosphorus atom in the middle, and they are doing essentially this. So they are making a quantum-enhanced estimate of a magnetic field using essentially this technique that I showed on the previous slide. Another example of quantum-enhanced sensing is LIGO. LIGO uses so-called squeezed states of light, where you're playing around with the uncertain relation to get enhanced sensitivity. So in 2011, they were trialing this, and it's part of the advanced LIGO. So they are enhancing their precision by using the quantumness of light. Finally, and this is the very last bit, I wanted to say something about quantum computing. So what's this picture? Protein folding. That's a very difficult thing to figure out, how a protein will fold into what shape. And it's an example where something like a quantum simulator, so if you can't calculate what it will do, build it and see what it will do, essentially. But not maybe exactly this molecule, but just some model of it that works, that behaves in the same way. And that's essentially what a quantum simulator is. So this is, I think, ions held in a lattice, pictures from NIST. So the idea with a quantum simulator is if you want to figure out how a material is working, say, is a material superconducting or not, that's very, very hard to compute. Another approach then might be to sort of build a model of it. So, but not the material itself, but you could have some sort of multi-purpose quantum simulator that you can tune parameters in, and you can then let it evolve and see what it does, instead of just trying to calculate what it would do. That's the idea behind a quantum simulator. And more generally, you can have quantum computers, and instead of classical bits that can be either 0 or 1, you'd have quantum bits or qubits, which can be in superposition. So they could be atoms or ions or photons or something like that. And then a quantum computer then can do certain things, better than classical computers. Typically, because you can use these superposition states. So you can essentially start with your computation in a superposition of all different kinds of input data. But you have to be clever, because when you measure at the end to learn your result, you only get one result. So you have to make those different sets of input data interfere in just the right way for you to learn exactly what you're after quicker than with a normal computer. So there are a few examples of cases where we know so-called quantum algorithms for things that a quantum computer would be better at than a classical computer. One is factoring numbers. Maybe the most famous example. But probably quantum simulation is the first kind of cases where you might be able to see some benefit of quantum computers. So people are trying to build these things. Nothing has yet been shown to work better than or faster than a classical computer, but you might be getting there in the next 5 to 10 years, unless that's too optimistic. So, final slide, more or less. I want to plug this Blackett report on quantum technology in case you want to learn more about what the second revolution of quantum technology might do for us. I was part of writing this report earlier this autumn, and you can get it from the UK government website. It explains to you sort of all different kinds of things: clocks, imaging, sensing and measurement, computing and simulation, communication. What kind of new applications might we expect from quantum technology in the next 5, 10, 15, 20 years? So with that, I'd like to finish. I'm going to put up a last slide. So during the reception, I have a hobby. I sort of write physics texts to songs. So this is a selection of the songs that might be available for performance if somebody's interested. So thank you.